We're very pleased that Eric Lerner is going to make a presentation today about the race to fusion energy, reality versus hype. He's been active in fusion research for about 40 years. Back in 1984, he developed a detailed quantitative theory for the functioning of the dense plasma focus and continued his work in that area. He had a contract from the Jet Propulsion Laboratory. And back in 2003, he founded this company, LPP Fusion. At the time, it was the fourth fusion company to be founded and is a leading research company in the subject of fusion. Eric's also been leader in cosmological research as a developer of a non-expanding, non-Big Bang theory of the evolution of the universe. And his book out is called The Big Bang Never Happened. Eric, it's all yours.
Today, we're going to discuss the race to fusion, reality versus the hype. And we're going to start with the reality and leave the hype to the end. Well, why do we need fusion energy? I don't think it's news to any of you that humanity is in a crisis. It's not just the current headlines, it's been building for some time. This graph shows, on the one hand, the rate of increase of per capita energy. That's the orange line over the period since the Second World War. And you see the peak of development. The fastest development was way back in the 1960s. The 60s really were the good old days. And then there was a sharp decline during the 70s to a lower level of growth through the final decades of the 20th century. And then with the pandemic, there was a transition to negative growth, to contraction. And if we trace the rate of fall in the mortality rate as an indication of standard of living, it traces a very similar path to the development of energy. Tired of inflation, wars, and inequality caused by the energy crisis? LPP Fusion is developing a solution that could allow everyone to have cheap, clean, off-grid, and sustainable fusion energy. Invest now as we seek to bring this potentially life-changing technology to market. For more information, visit wefunder.com/LPPFusion. So again, we see the same pattern. Rapid fall in mortality rate, rapid rise in life expectancy, slowing down during the 70s, and then taking a plunge into negative territory since the pandemic. So over the past 6 years, the mortality rate for humanity as a whole has actually been rising. So this is a real crisis. And it is tied up with energy. We can't resolve this crisis. We can't provide an increasing standard of living to humanity with fossil fuels. Already fossil fuels, through fossil fuel pollution, killing 7 million dead per year by WHO estimates. The cost of fossil fuels is $5 trillion per year. Direct costs. It takes a tremendous amount of fossil fuels to produce the energy at present. 14 billion tons per year for all of humanity, which is 700 tons per year per megawatt of total power. That's total power measured in megawatts, not just electrical. So we need higher energy density. Sources that give more energy per unit mass, per unit dollar, cheaper, clean energy that's safe and unlimited. Solar and wind are also dilute energy because the energy we get from the sun is diluted by the time it reaches us. On average, it takes about 1,000 tons of material to produce a megawatt of power for solar and wind.
Wow.
If we were transitioning to pure solar and wind, which really wouldn't be possible, you need about 1 billion tons per year or more than $5 trillion per year in investment. The only real route available to getting the energy we need much more cheaply than present is fusion energy. Now, fusion energy on a cosmic scale is very common. It's the power that drives the universe. This is the energy source of our sun and all the stars in the sky. It's the densest form of energy we know, densest in terms of power per unit mass. As people have pointed out in the earlier discussion, this is a power source very different than fission. Fusion energy occurs when you combine two charged nuclei, and they react and produce either charged nuclei or charged nuclei and neutrons. We'll discuss that as we go along. So it's the input that creates the fusion description. In contrast, fission always requires as input one nucleus and a neutron.
Right.
Neutrons have to be part of the input. It's a big difference because fission always produces neutrons as the output. That's the energy, and a lot of radioactive waste because the fission process can't be precisely controlled. You get what nature gives you in the fission process. In the fusion process, you can determine what the products are for a given fuel. There are several different approaches to fusion, and the biggest difference among the approaches is the fusion fuel used. Up until now, most effort has gone into fusion fuels that are based on deuterium. Now, deuterium is quite common in seawater. It is the isotope of hydrogen that has a single neutron and a single proton. Ordinary hydrogen, just one proton. So a deuterium nucleus combined with a tritium nucleus, the third isotope of hydrogen, combines to produce a fusion reaction that gives helium and a neutron as products. The other alternative is hydrogen and boron, which is becoming more and more popular, although still a fraction of the effort going into DT. So basically what we start with is a proton and a boron-11 nucleus, and those combine to produce 3 helium nuclei. And what's important, no neutrons in the primary reaction. So we'll describe these different approaches in more detail. A DT fusion, first of all, needs a complex breeder because tritium does not exist in nature. Tritium is radioactive with a half-life of 12 years. So it doesn't exist in nature, and you have to breed it. Now, right now, with no fusion industry based on DT existing, you get the tritium as a byproduct of a fission reaction. So it's right now people are experimenting with tritium that's been produced by non-fusion means. But theoretically, you can get a breeder reaction, and that's what's shown here. So the tritium produces a neutron. The neutron goes to a wall of beryllium. The beryllium produces 2 neutrons and another helium nuclei. And each of those neutrons goes to a lithium blanket, which then produces 2 tritium. So you can have a breeding reaction in which 1 tritium of input produces 2 tritium of output. So this can be a sustained reaction, but it's quite complicated. If you look at the size of this building, this is the building that's being constructed at the ITER facility in southern France. just to process the tritium, you can get an idea this isn't a cheap process. In addition, of course, you do have a big neutron flux. So that neutron flux has to be diluted because it does enormous amount of damage to your structure. So that's one reason why machines that are based on DT themselves have to be quite large. But there's another reason why DT machines can't really be cheaper than existing fusion, which is they release their energy in the form of a neutron. And there's no known way of getting energy out of a neutron except the same way as Edison developed more than a century ago, which is to use the neutron to produce steam, to drive a turbine, to drive a generator. And turbines themselves are very heavy, expensive pieces of equipment. So the capital just in energy conversion is more than $1 per watt. So it's more than the cheapest energy available today, which has a total capital cost of about $1 per watt. Another way of measuring it is 7 tons per megawatt. So those are some reasons why the machines that are based on DT are bound to be large and expensive. Now, PB11 has several big advantages. First of all, it is the highest energy density of any naturally occurring fuel. Boron 11 is 80% of natural boron. It's a stable element, very abundant in nature. It's a significant component of sea salt. Hydrogen, obviously, is the major component of ordinary water. So we have abundant raw materials. There is no radioactive waste. Radioactive waste is defined as a radioactive level that is dangerous to human beings. Radioactivity is everywhere. We're radioactive ourselves. But radioactive waste is at a level that's dangerous to our health. And no radioactive waste is produced by burning PB11. As I say, the main reaction produces nothing but pure helium. And there are side reactions at a very low level, which do produce a tiny amount of carbon-11, which is radioactive with a very short half-life, 20 minutes. So would decay back to nothing as soon as the machine is turned off after about 10 hours. Equally important, because the products produced are electrically charged and moving electric charges are electricity, we can convert the energy directly to electricity with no turbines, no generators, no necessity to turn the energy first into heat. And of course, there's no neutron damage. All of this adds up to the fact that you can have energy conversion that's far cheaper than existing energy sources. So in our device, for example, we've designed an energy conversion which is less than 0.2 tons per megawatt, or a total cost of about investment cost in the direct conversion of about 3 cents per watt, again, compared with 7 tons per megawatt and $1 per watt for the conventional turbines that would have to be used with DT. So that's one reason why, of these two approaches in terms of fuels, the fuel to go with is, in fact, PB11, boron fusion instead of deuterium fusion. Now, there's a second main division in the approaches to fusion, which is devices that use an external magnetic field to confine the hot plasma where the fusion takes place. Now, plasma is just electrically conducting gas. It's the dominant phase of matter in the universe, but not here on Earth. So in the external magnetic field approach, you use artificial magnets around the outside of the machine to produce the magnetic field. In the internal magnetic field approach, we use the pinch effect, where magnetic fields produced by currents pinch the currents together to get high-density plasma. And this shows the main types of device, which we'll, again, go into in more detail in a bit. So the main types of device for the external magnetic field are the tokamak, where the most effort has gone into, the stellarator, and the field reverse configuration. We'll get into the high density in a minute. That's our type of device. We work with the dense plasma focus at LPP Fusion, the laser, and the Z-pinch. If you look at this fourfold division of low density, high density, deuterium, and hydrogen-boron, you can basically see the companies that are working in these various divisions. Now, this isn't a complete list. There are already 45 companies around the world working for fusion, but these are the most prominent. So as you can see, companies that you may have heard of, Helion is low density, TAE, ENN, you probably haven't heard of, but it's the giant natural gas energy company in China. And on the high density side, there are almost certainly companies that you haven't heard of. So working with deuterium is MIFTY and Zap Energy. And then these are the only three companies working in high density and with PB11 is our company, LPP Fusion, HB11, which is located in Australia, and Marvel, which is in Germany. The external magnetic field devices, regardless of the fuel, are also large, expensive machines. Now, it takes a bit of a story to get to why this is the case, but I don't think it's too complicated. First of all, you have to realize that there are technological limits on external magnetic field strength. These aren't limits based in nature. This is limits based in how far engineers and scientists have advanced in improving the magnetic field that the magnets themselves can withstand. Right now, that limit is about 12 Tesla. For comparison, your standard MRI scanner that maybe you've been scanned with, that's going to be about 3 or 4 Tesla. Now, the magnetic field strength limits the plasma density because the pressure applied by the magnetic field goes as B squared, magnetic field squared, and the outward pressure generated by the plasma goes as the density times the temperature. Now, you need a certain temperature to burn these fuels. For DT, you need 40 keV. That's 400 million degrees, or 400 times the temperature in the center of the, 40 times the center of the sun. For PB11, you need even higher temperature, 6 billion degrees. So those temperatures are fixed, and that means that the magnetic field limits the density, and it limits it quite a bit to a billionth the density of water for DT and to a 10 billionth the density of water for PB11 because the temperature is higher. Now, if you have the lower the density, the longer the path that a nucleus has to travel to have a fusion reaction. At these very low densities, the nucleus has to travel a long ways. For DT, 10,000 kilometers, and for PB11, 800,000 kilometers. That's 3 times the distance to the moon. So obviously, in a practical-sized device, You have to make the nuclei go round and round and round and round, many revolutions before fusion occurs. The next thing you have to understand is that plasmas are naturally unstable. So plasmas are unstable throughout nature because there are many processes that lead to inhomogeneities. The biggest is the pinch effect. So the pinch effect means that currents moving in the same direction attract each other through their magnetic fields. Currents moving in opposite directions repel each other. So there tends to be filamentation, the creation of little vortices throughout. And if you're trying to keep the plasma stable, this basically limits the lifetime of the plasma. And starting with Nobel laureate Hannes Alfvén back in the 70s, we learn that at all scales throughout the universe, from a solar flare up to the scale of a galaxy, plasmas in nature only undergo a small number of revolutions, dozens, hundreds, or at most 1,000 revolutions. Here on Earth, just recently in the last year, researchers working with the East tokamak in China and the West tokamak in France were able, with active feedback, to extend the lifetimes of plasmas for the first time beyond those natural limits, up to about 300,000 revolutions. But it's going to be very, very difficult to get beyond that limit. So if you divide 10,000 kilometers by 300,000 revolutions, you get 30 meters, or a radius of 5 meters, which gives you the necessary scale, minimum scale, for fusion devices that are based on external magnetic fields. Again, very large, heavy machines. And if you look at the plans for these machines, for example, there's the BEST machine, modestly titled by the Chinese. The BEST machine is 3.6 meters in radius. Well, that's the radius of the plasma. The machine that contains the plasma is a good deal larger. If you can see in the left-hand image, the small images of the people to the right of that image, you can get some idea of the scale, and the total building size is evident on the right. That's not just true of the Chinese. There's the planned ARC device, which is planned to be built by Commonwealth Fusion Systems in Massachusetts. They've given details of their plan. So again, a very heavy device, 40 tons per megawatt, and a very expensive device, $30 per watt, way beyond the current energy sources that we rely on today. If you have PB11 with this external magnetic field approach, the confinement is a lot more difficult. You do have the advantages that you don't have the complexities of tritium breeding because you're using natural fuel, but the confinement is much worse because you're using lower density and higher temperatures. So you would need 35 million revolutions with existing magnets, which is probably impossible to obtain. That's basically absolute stability, which occurs nowhere in nature. Or you need to do the research, which would probably take many years, perhaps decades, to get 10 to 20 times higher magnetic fields. And it's taken decades to get to 12. Again, TIAA estimates their own cost of $4 per watt, and that's probably quite optimistic, but again, not equal to what can be obtained today with conventional sources. So basically that means external magnetic field devices can't have capital costs less than existing sources, but The other approach, internal magnetic fields, no surprise, it can. With magnetic fields produced by currents within the plasma, there is no limit on the magnetic field. The magnetic field is only limited by how small the radius is. So for a given current, the smaller the radius, the larger the magnetic field, inversely proportional. We've obtained experimental evidence of fields as high as 4 kilotesla. So that's thousands of times stronger than with external magnetic fields. And our predecessors, my mentors in this field, Bostic and Nardi, they achieved 40 kilotesla. Our colleagues using lasers, producing ion beams, which I'll describe in a minute, they get 10 kilotesla. We're aiming for much higher. We think we can get much better compression and get up to 500 kilotesla. So that's no limits on the density. And with much higher magnetic fields, you get much higher density. The results we've already obtained are approximately 1/10,000th of water density. And we're aiming for a goal of about 1/10th of water density instead of billionths of water density. And this is an example of an image we've taken with an ICCD camera with an exposure time of less than a nanosecond. This is a plasmoid that's created within our device, and you can see we can already squeeze these down to essentially hundreds of microns in radius. And we hope to do much better. So a small plasma allows a very small number of revolutions. So we're aiming for metastability as in nature. Now, why is this the case? It's a number of pretty simple algebraic steps. The distance to a fusion reaction is 1 over n, 1 over the density. The density goes as the magnetic field squared. And the magnetic field goes up as 1 over the radius. So the distance that you need to travel to get to a fusion reaction goes as the radius squared. So the smaller the radius, the distance you need to be traveling goes down as the square. The ratio of the distance to the radius of the plasma, the number of revolutions, therefore is proportional to radius. So the smaller the radius, the smaller number of revolutions to get to fusion. So that means that with our device, we need thousands of revolutions, as in nature, not hundreds of thousands or millions. So this means with these very small metastable plasmas, the size of the device is basically disconnected from the plasma. It's going to be larger than the plasma, but it's going to be controlled by engineering features such as how much cooling do you need, how much energy can you take out of how little space, and similar considerations. We don't have to worry about neutron damage because we're not producing any neutrons. The net result is very small, very light, and very cheap devices. So the device we have planned, which would be a 5 megawatt generator, would be about 0.6 tons per megawatt for the entire device and about 10 cents per watt for the entire capital investment. So that means with these kinds of devices, you can have a transition to fusion at the same time vastly slashing energy costs. Now, that's with the combination of high energy density, internal magnetic fields, and PB11 fuel. These advantages are very much diluted if you stick to deuterium-tritium, because then you have the high cost of conversion and you have to make the device large enough that it won't be damaged by the neutrons. So basically, the bottom line here is that only the machines that have only internal magnetic fields and are working with PB11 hydrogen-boron fuel have a chance of giving us that cheap energy that humanity needs. So let me go into briefly the three approaches to getting hydrogen-boron fusion at high density. The first one is laser-generated proton beams. So in this approach, unlike what you may have heard of at the National Ignition Facility, you're not using the laser to directly heat the plasma. You're using the laser to produce a proton beam. And the way this is done is kind of clever. This was envisioned in the 70s by John Dawson, and then was developed at the end of the 20th century and the beginning of this century by several researchers. You take a very powerful laser, picosecond or femtosecond laser, and you concentrate it on a gold foil. So this produces a ball of plasma in which the electrons, being lighter, move away more quickly, in fact, at relativistic speeds. So you have a hot electron cloud, and that produces a huge electrical field that accelerates the protons into a beam as they try to catch up with the electrons. Now that is used in what's called a pitcher-catcher approach. So the pitcher, as in baseball, generates the proton beam, and it's directed at a second target that contains boron. So the proton beam then interacts with the boron to produce the fusion reactions. So there are big advantages to this approach. First of all, there are big lasers in existence, so you don't have to build a device to do the preliminary experiments. They're not adequate to reach net energy, but they are adequate for these experiments, and that's why the companies using these have been the first to get actual fusion results with PB11 fuel. And you're starting at solid density, so you don't have to necessarily have any compression to reach high densities. Now, the big disadvantage is that these lasers are highly inefficient. So typically 1% of the laser energy, the electrical energy input to the lasers is converted to light, and the light only creates the proton beam at 10% efficiency. So you have to produce far more fusion than the energy provided by the beam, thousands of times, to get net energy. Now, that's a disadvantage, but it's not a killer, because the amount of energy you get out of the catcher, the pellet, depends really on the size of the pellet. The idea is to produce a continuous burn front that will heat the plasma from fusion energy to the temperatures needed for fusion energy, and you will have the burn extend all the way through the pellet before it has time to disassemble. So you could produce much more energy than is fed in and potentially get net energy. Even though these lasers are expensive, because the pellet can be built larger, you can potentially have large machines, but that nonetheless have capital costs lower than existing energy sources. So this is a possible route, but when you have to build these lasers custom built for fusion, that's going to take a long time. They are hundreds of millions of dollars device. The Z-pinch is very simple to explain. The Z-pinch is just, you take a plasma like the one on the left, and you shoot a lot of current through it suddenly. So then the pinch forces pinch it together in two directions, as on the right. So then you get compression, heating, and fusion energy. The disadvantage is that because you're only compressing in two directions, it takes a lot of energy to reach high density. So for example, the Z machine, the biggest pinch machine in the world, is a very large machine, but the maximum density they've achieved is about 1/1000th that of air. By comparison, our little device, which fits in a garage, has achieved densities 1/3 that of air. And we use thousands of times less energy than the Z machine. So finally, leaving the best to last, it's the dense plasma focus, which is the device we've been using. We didn't invent this device. It was invented simultaneously in the Soviet Union and the United States back in the 1960s. But it has several key advantages. It is far cheaper and far smaller than any other potential energy source. So that's the actual electrodes that we're using in our device, and you can see my colleague Ivy's hands by comparison. This is a very small device. You can really hold in your hands the heart of the device, which are the electrodes. Instead of fighting the instabilities of plasma behavior, we use those natural instabilities. And because it's so small, it's ideal for decentralized power and even for portable uses, such as in ships or potentially even aircraft. Again, this is our conceptual device, which is not a lot larger, or really any larger, than our existing experimental device, which is in Middlesex, New Jersey, and fits in a room that is 13 by 13 on a side. As I say, we imitate the processes in nature, and this is one of the links to my additional research in cosmology. The mathematical scaling laws that we use in developing this device actually came from using it as a model for the quasar explosions in deep space. So let me show you how it works. So the first step is that we dump energy from capacitors into a vacuum chamber with the fuel in a gaseous state. And that sends the electricity between the cathode, which is the outer ring, and the anode, which is inner. Through the Prince effect, we create evenly spaced filaments, which is the first stage in compression and heating. So in the second stage, we're going to say the second pinch effect pinches all these filaments into a single filament, which starts to kink up into a three-dimensional object called a plasma. This is all based on extensive observation. That heats the plasma up to fusion temperature, where the hydrogen-boron reactions take place. We've achieved 260 keV, that's 2.6 billion degrees, and published that in peer-reviewed journals. Now, the device also produces, as this plasmoid decays, beams with the ions going in one direction and the electrons going into the other. So that means we have a convenient way of converting the beam by simple electrical induction into a current in a circuit. And that's the way we get the energy out. To sum up this section, what we're talking about is there's a cheaper and easier path to fusion, which is using internal fields and PB11. We think that our device is the easiest of among the three devices to fusion. So that's what the path looks like.